Hello, my dear students. A very good morning to everybody. Let's continue our discussion on Newton's laws of motion. What we had discussed in the last class was about Newton's first law of motion and linear momentum. We have just discussed about the statement of Newton's third law of motion, right? Now, along with the statement and lot of information related to the linear momentum and few numericals related to the Newton's second law of motion, we will be discussing today. The complete today's session is related to Newton's second law of motion. So let's begin the class. What we will be learning here about a linear momentum and Newton's second law of motion. I hope everybody is ready for the session. Now, linear momentum. In a brief, what we had discussed. It was the quantity of motion contained in a body. So to measure this quantity of motion, both physical quantities are very important. Both the physical quantities are a mass into a velocity. And you know the SI unit of the linear momentum is kg meters per second. And this is the linear momentum, which is a vector quantity. These are all the things we had already learned. So it is a vector quantity, right? So when linear momentum units are kg meter per second, so the same units will be there for the change in linear momentum. Lm means linear momentum. Change in linear momentum SI units is also equal to the linear momentum SI units. Okay, clear? Now, so linear momentum m into v, and we had already discussed delta p, which is equal to change in linear momentum, which is final linear momentum minus initial linear momentum. That's called change in linear momentum. Okay, fine. Now, let's see the basic problems related to the linear momentum will be like this. So there is a body of mass 1500 kilogram, right? So look at here. So there is a body of mass 1500 kilogram, huge mass, right? It is moving on a straight line with a constant velocity 72 kilometers per hour. Now the question is, find the linear momentum in this case. This is a basic question related to the linear momentum. So as the linear momentum formula, we have mass into velocity, where mass is 1500 kilogram into where velocity is given as 72 kilometer per hour. Most of the students of 10th standard and 9th standard, they just directly multiply these two quantities and get the answer. So 100% that's a wrong answer, because this is kilogram, which is the SI unit. So this is the kilometer per hour. So what is this quantity? It is the speed. Speed SI units are meter per second. But this kilometer per hour is the unit which is not the SI unit, which is the bigger units of speed. That's it. It's not at all the SI unit. So when you are multiplying or dividing two or three physical quantities, so remember carefully, all the physical quantities must have similar system of units, right? So if it is in grams, the speed units must be in centimeter per second. If it is in kilogram, the speed unit must be in meter per second. Okay, so our first aim is to convert this kilometer per hour into meter per second, and let's convert it. So 1500 kilogram into 72 into 1 kilometer per hour is equal to how much? It is equal to 5 by 18 meters per second. Okay, so this 18 fours are 72. So what I can write? 1500 kilogram into 20 meters per second. Okay, clear? So now what is remained? I am writing carefully. See, it is 15 and it is 2. Okay, 15 twos are 30 and how many zeros are left? 1, 2, 3. 1, 2, 3. 3 zeros are left. So total 30,000 kg meter per second. If you want to represent it in terms of 10 to the power some values, so this I can write it as 3 into 10 to the power 1, 2, 3, 4. 3 into 10 to the power 4 kg meter per second. Our linear momentum will be in SI units, which is kg meter per second, right? So this is the final answer. Like this, the basics questions will be asked, right? So now, during the linear momentum topic, what is the point we had discussed was linear momentum can be transferred. Linear momentum can be transferred. What exactly meant by the linear momentum can be transferred, we will be discussing now. Listen to me carefully. So look at this example. Look at this example. A body of mass, a small mass 10 kilogram, which is dropped. Dropped means its initial velocity is 0. Yes or no? Dropped means its initial velocity is 0. So when it is dropped here, carefully see. So this is the ground, right? So from the ground, it is at a height of 80 centimeters and it is dropped in this way, right? So as the initial velocity is 0, initial linear momentum is 0 here. Clear? As the body is moving towards the ground, it will increase its linear momentum associated with this, because our linear momentum is equal to mass into velocity. Mass of a body is constant in this way from this point to the ground. As the mass is traveling towards the ground, it remains constant, and velocity. Tell me, when the body is freely falling in this direction, so will the velocity remain constant or increases or decreases? I hope you understand the question. When a body is freely falling towards the ground, tell me about its velocity, whether it increases or decreases or remains constant. So definitely the speed will increase, speed of the body will increase gradually when it is moving towards the ground. So the same thing happens here. So when mass remains constant, so the linear momentum is directly proportional to the velocity. When velocity is increasing, the linear momentum also will increases. Clear? So the linear momentum increases. I'm writing here, the linear momentum increases. And at this point, just before striking the ground, so that's called the final linear momentum of a body. How much? Look at here. This is the final linear momentum of a body, which is m into v. M is mass of the body, 10 kg. And what is the velocity? Velocity before striking the ground. So from the equations of motion, you can find that velocity. Okay. Now, what is the point we are going to discuss? The question is, there is a dumbbell. For example, this is not a ball, this is the dumbbell. So there is a dumbbell of mass 10 kg, which is dropped from a height of 80 centimeters. Now the question is, find the linear momentum transferred by the dumbbell to the ground. So that's the question. Find the linear momentum transferred by the dumbbell to the ground. Imagine you have a ground which is covered with a glass surface. Listen to me carefully. So I have the similar case of dumbbell of 10 kg here. Your ground is covered with the glass surface. If I drop this dumbbell, what happens after some time? So definitely the glass will break on the ground. Yes or no? 100% it is yes. Why? That's the question, right? Because as the body is freely falling towards the ground, its velocity will be increases. So that means the linear momentum of the body increases, and at this point of striking, the body will have some quantity of motion. Yes or no? That's called linear momentum. So that quantity of motion will be transferred to this glass. Right? But the glass material cannot hold that much amount of quantity of motion contained. So that's the reason it will break. Okay? Clear? So, how much is the linear momentum will be transferred by the dumbbell to the ground? That's the question. How much it will be transferred? How much it will be having at the point of striking, the same amount will be transferred. That's it. So now at this point, find out the linear momentum. So that amount will be transferred to the ground. So how to find the linear momentum at this point? Mass, we have 10 kg, and V. To find V, we can use the equations of motion. To use the equations of motion, what are the physical quantities we have? See, for example, equations of motion, let me write. It will be a revision for most of the students who have joined recently. So, equations of motion, we have three. Basically, the majorly three equations of motion we have. So, V is equal to U plus AT, S is equal to UT plus half AT square, and third one is V square minus U square is equal to 2AS. Okay. Now, in first two equations you see, our aim is to find what? Final velocity. Okay. So, in the second equation, is there any final velocity? No. There is no final velocity term even. And the first equation, is there any final velocity term? Yes, there is a final velocity term V. And in the third equation, is there any final velocity term? Yes, there is a final velocity term. But is there any time values are given in the given question? No, not at all mentioned. So, first equation, time is the quantity is there, which is included in this equation. That's why I have just eliminated the first equation and concentrate on the third equation. So, this is the equation suitable for us to find a V, because they have clearly given in the same question, take G value as 10 meter per second square and solve the question. So, here this equation can be written as V square minus U square is equal to 2 into acceleration due to gravity is G into S is the distance covered from here to here is H. Okay. So, from this, as initial velocity is 0, meters per second. So what I can write? So V square is equal to, see here, U square will become 0, right? So V square is equal to 2GH. So from here, V is equal to square root 2GH. So our aim is to find linear momentum just before striking the ground. So I am writing here linear momentum before striking the ground. Linear momentum before striking the ground, P is equal to M into V, where M into V is square root 2GH. Just substitute everything, you get the answer. P is equal to mass is 10 kilogram into square root 2 into G. G is what here? They have clearly mentioned it is 10, right? Into H. H, you carefully see, they have mentioned as 80 centimeters. I told you in the previous problem. 99% of the students, not only you, these are called the silly mistakes. By overlook and overconfidence, the students generally make silly mistakes. And see, I've seen some students who are in 12th standard and making the silly mistakes like this. Not even in the 12th standard, after finishing in the 12th standard, the long-term students also used to make this kind of small mistake. And what is the mistake is that is, so 80 centimeters is given, whereas mass is written in kilogram and G is written in meter per second square, means everything is written in SI unit, but The height they had mentioned in 80 centimeters. So you need to convert this into the meters. That is 80 into 10 raised to minus 2 meters. Okay. So now what I can write, height is 80 into 10 raised to minus 2. So this I can write 80 by 100. Understand? 80 by 100. Clear? So here 1 0 1 0. Another 0, another 0 cancelled. So P is equal to 10 into square root 2 into 8, that is 60. So what I can write? It is 10 into 4, it's 40. And what is the SI unit of linear momentum? SI unit of linear momentum is 40 kg meters per second. That's it. So this is the linear momentum of a body before striking the ground. And this much amount will be transferred to the ground. Okay. So now once again I'll just revise the question what exactly they have asked. So the question was, there was a ball of mass 10 kg, a dumbbell of mass 10 kg, which is dropped from a height of 80 centimeters. Find the linear momentum transferred by the dumbbell to the ground. How much? It is 40 kg meter per second. I hope it's very clear to you. Now we will be going deep into Newton's second law of motion. What was the Newton's second law of motion? What are the new things, new physical quantities involved in the statement, and further parts of the statement we will discuss. And remember about linear momentum itself. See, this is the linear momentum just to make you understand second law of motion we have discussed. So much information is still pending in the discussion of linear momentum. Later we will be doing that. So right now, Newton's second law of motion, we are going to start exactly. Alright, let's start. See, the second law of motion states, what was the second law of motion statement? It was the rate of change of linear momentum is directly proportional to the external unbalanced force, and it is in the direction of resultant force. And it is in the direction of what? Resultant force. Let's talk about one by one now. So better than the previous statement when I had written in the last class, you will understand it far better now. Let's see. Second law of motion, what is that? Rate of change of linear momentum. Rate of change of linear momentum. And before moving into this, I would like to tell you one basic example from the previous concepts of the motion chapter. What was that? So rate of change of velocity. What was the rate of change of velocity? Can anybody recollect what was the rate of change of velocity actually? The rate of change of velocity is the acceleration. What is that? So rate of change of velocity is what? Acceleration. So how rate of change of velocity becomes acceleration? Look at here. So rate of, forget about the rate of, because first time we are learning about the concept of rate. Forget about that. So but we know the change of velocity. So this is the part we already know called change in velocity. So what is the change in velocity? Final velocity minus initial velocity, right? So change in velocity you can represent with a symbol called delta V. What is that delta V? final velocity minus initial velocity. I am writing here. So I am explaining about rate of change of velocity first. So the rate of change of velocity is final velocity minus initial velocity. Okay, this is change of velocity. What about this rate? So rate means whatever the quantity it is mentioned here divided by time. That's it. It's so simple. Whatever the quantity is mentioned here divided by the time, that's called rate of that particular quantity. Here the quantity is not only the velocity, here the quantity is change of velocity. So that's important. What is that? That is most important. In the same way, so let us understand this one. Rate of change of linear momentum. And before that, see, change in velocity by time is what? Your acceleration only. Right? Same way, rate of change of linear momentum means change of linear momentum divided by time. Change of linear momentum divided by time. It's so simple. Now, let us understand the second law of motion, and we are going to derive the second law of motion. See here. So, this is the ground. There is a body of mass m moving with some initial velocity u. After some time, it has reached to the another place. Mass remains same with a final velocity v. Here, we need to imagine that the body is accelerating. The uniform acceleration is taking place from here to here. Uniform acceleration means speed will increases. Okay. So, the body is moving with uniform acceleration. Speed is increased. Now here, mass into initial velocity, I can write it as initial linear momentum, which is equal to mass into initial velocity. Here, final linear momentum, mass into final velocity. Okay. Now, from this, we already discussed in the last classes. So, change in linear momentum. Change in linear momentum is delta P, which is equal to final linear momentum minus initial linear momentum, which can also be written as m into v minus m into u. So, change in linear momentum delta P is equal to m into v minus u. Clear? This is change in linear momentum. It's very clear. What is our aim? Our aim is to find an expression for second law of motion. What is that? Expression which will be explaining Newton's second law of motion. We are going to do that. For that, rate of change of linear momentum we are going to check. But we got change of linear momentum. When change of linear momentum you have got, just divided by time, you get the rate of change of linear momentum. Yes or no? It's similar to this case. So, what I am writing here is the rate of change of a linear momentum is equal to, what is that? Delta P divided by time. That's it. Right? So, finally, what I am writing? Rate of change of linear momentum is m into v minus u by t. So, this is the most important part of the statement of Newton's second law of motion. The rate of change of linear momentum is m into v minus u by t. Clear? Sure? Are you understanding? Now, the rate of change of linear momentum is directly proportional to the external unbalanced force. Here, the body is moving with some constant acceleration, means definitely there must be a force applied on this body. Okay. Because of that force only, the body is getting accelerated. So that's the concept of dynamics. Dynamics is the branch of physics in which we study about the motion of a body by considering the cause of the motion. What's the cause of the motion? The cause of the motion is force. Okay, clear? So, this is the force. External unbalanced force. This is the external unbalanced force. And external forces only can accelerate the body. I have given wonderful examples in the last class. External forces only can accelerate the body. Internal forces cannot accelerate the body. Right? Now, The rate of change of linear momentum is directly proportional to the external unbalanced force. So this is our external unbalanced force. Okay, so I am writing here. So F, we are imagining that F is an external unbalanced force. External unbalanced force. Listen to me now. Generally, we will be applying so many forces in our daily life. So not so many forces, so many times we will be applying forces on different bodies around us in a daily life. For example, to move one object to the another object, so we will be applying some pulling force. So to close the door or to open the door, we need to apply some force. Understand? So to press something, we need to apply the force. To throw something, we need to apply the force. All of these forces. And all the forces are external unbalanced forces only, because through which the acceleration of the body is taking place, all those forces comes under external unbalanced forces. Okay? And 99% of the cases in our daily life where we are applying forces, those are external unbalanced forces only. Suppose, if I ask you, go there, use some external unbalanced force to open the door. If I say something like this, will you be understanding the concept here? You'll definitely laugh. Alright? You'll definitely laugh if I say that open the door by using an external unbalanced force. Understand? So what general language we use is just by applying force, open the door, it will come out. Okay, so that force, generally we term as a force, that force is equal to external unbalanced force in the nature. Okay, so now the rate of change of linear momentum is directly proportional to this external unbalanced force. And so let's write this relation. So rate of change of linear momentum, so I am writing here, according to the statement of what? Newton's third law or first law or second law? Second law, according to the statement. So the rate of change of linear momentum, I can write delta P by T, which is rate of change of linear momentum is directly proportional to what? External unbalanced force F. So this I can write in this way. Delta P is m into V minus U divided by T, which is directly proportional to F. So this I can also write it in this way. F is directly proportional to m into V minus U divided by T. Okay, and one more time. So this F can be written as, which is directly proportional to m into V minus U by T. Okay, so now F is directly proportional to m into, what is this V minus U by T? That's acceleration of the body. Understand? So because of this external unbalanced force, what is the acceleration provided in the body is A. Acceleration produced in the body is A. So now this I can write F. If I want to remove the proportional symbol, I need to write is equal to, and there is a constant K. So into M into A. For example, if K is a constant having the value called 1, that's experimental value. K is 1. Then your F is equal to a mass into acceleration. F is equal to what? Mass into acceleration. So look at this interesting relation. F is equal to MA. If I ask the student who have just finished their 10th standard or even the 12th standard, remember, if I ask them what is the Newton's second law of motion, 99% of the students will tell me F is equal to MA. F is equal to MA is not at all the Newton's second law of motion statement. Okay, it is the expression what we have got from statement of second law of motion. It's a final expression. It is not the second law of motion. Okay, second law of motion statement is here. You can read it one time, two times, three times, n number of times you must read the definition, because you see, you understand, last class duration was about 47 minutes. So 47 minutes we had discussed about Newton's first law of motion, right? You can believe 47 minutes related to the first law of motion is very less, you know. So the minimum, if we want to discuss related to the first law of motion statements, it takes minimum 3-4 hours. But as less as possible, so we are just doing here. Now, second law of motion is also similar. Lot of information is related, lot of information is available within the definition itself. Okay, now slowly from the basics to the middle level to the higher level, we will be moving in terms of numericals even. Now, F is equal to MA, we have got it. So from here, F is equal to MA. Look at the interesting part. Let's concentrate on SI unit, for example, here itself. So F, mass is kilogram into acceleration, meter per second square, which is equal to 1 Newton. Okay, 1 Newton is equal to SI unit I am talking about. SI unit of force is 1 Newton, which is 1 kg meter per second square. Right? Now, if the mass is written in grams and acceleration is given in centimeter per second square, and this is equal to dyne. 1 dyne is equal to what? Gram centimeter per second square. So the relation between these two will be 1 Newton is equal to 10 raised to 5 dyne. Okay, so keep this in your mind, which we had already learned. 1 Newton is equal to what? 10 raised to 5 dyne. Right. All right. Now, Newton's first law can be derived from second law. That's the most important part of this second law of motion discussion. Newton's first law can be derived from second law. How? How come it's possible? Let's see. We have F is equal to MA, right? Imagine the acceleration is 0. Acceleration is 0 meter per second square. When acceleration is 0, force acting on a body is equal to 0. Force means the net force acting on a body is 0. And come back to the diagram here. Here there is one force is acting. When there are two forces acting, you can find the resultant force. When there are 4 forces acting, you can find the resultant force. And you know how to find the resultant force. But here, only one force is acting on the body. That one force is called the resultant force. Okay. So F is the resultant force. And when the resultant force acting on a body, so the body can exist in two states. One is the state of rest and another one is the state of uniform motion. Okay. Clear? So the first law of motion states that every body continues to be in the state of rest or continues to be in the state of uniform motion unless it is acted upon by an external force. Clear? As long as external force is 0, the body will want to be in the state of rest or it wants to be continue in the state of uniform motion. That's it. So this is second law and we derived about first law. So first law of motion can be derived from second law of motion. Clear? So this is about Newton's second law of motion, and before going to conclude the Newton's second law of motion, a small part of the definition we have not discussed. So we must do that. So, and it is directed in the direction of the resultant force. What is the meaning of it here? It means the rate of change of linear momentum. So, linear momentum is a vector quantity. Change of linear momentum is also a vector quantity. Is it clear? Rate of change of linear momentum is a vector quantity, and that vector quantity will have its direction. That direction will be always in the direction of resultant force. Right? If the resultant force acting on a body towards left side, that rate of change of linear momentum also will be in the left side. If the resultant force acting on the body in the right side, your rate of change of linear momentum also will be in the rightward direction. So that's the concept of Newton's second law of motion. Look at the basic numerical related to Newton's second law of motion. Newton's second law of motion is not yet finished. Today we will be concluding with this numerical, and next session will be complete numericals related to the Newton's second law of motion. There is no hurry for us to rush with the Newton's laws of motion, right? That's the reason. In detailed analysis of Newton's first law, second law and third law we will be doing along with the numericals. So let's see. A bus starts from rest. Bus is starting from rest. So this is starting from rest. Means what? Initial velocity is 0 meters per second. Okay. And it's moving with a constant acceleration. So the acceleration is given as constant. Okay. Now it is traveling a distance of 200 meters in 10 seconds. Given, so distance traveled is given as 200 meters and time is given as 10 seconds. And mass of the bus is given, which is 5,000 kilogram. We need to find then what will be the acceleration and force acting on it. What will be the acceleration and force acting on it. So the aim of ours to find the force and acceleration. So first the acceleration we need to find the force, because what is the formula at the end of the Newton's second law of motion we had learned? F is equal to m into a. Okay. To find F we have already m and we need a. How to find a here? I told you already in the last classes. A body is moving with constant acceleration. Immediately you can take the use of equations of motion. I hope you could recollect the topic. Equations of motion are valid and can be used when the body is moving with uniform acceleration, means constant acceleration. Okay. Now, by using equations of motion, how we can find acceleration here? We have initial velocity, we have displacement or distance and time. Which equation of motion I can use? Can I use first equation of motion? And let's see, V is equal to U plus AT. Can I use this equation to find acceleration? Tell me. Impossible. We cannot use this because V we don't know, U we know, A we need to find out, and T is given. So there are two unknowns, you can see V and A. So you cannot find the equation. So I can use S is equal to UT plus half AT square. Okay. So U into T is 0. Okay. So S is given as 200, which is equal to, this is 0, half into acceleration we need to find out, into T square. T square is 10 square is 100. So two zeros cancel here. So what is the acceleration we have got? So 2 into 2, it's 4 meters per second square. So once you find the acceleration, and it is very easy and simple for us to find the force acting on that bus. F is equal to ma, right? So what is the force acting on the bus? F is equal to, m is ma, m is 5,000 kilogram into acceleration is 4 meters per second square. You see here, no need of conversion of units here, because this kilogram is SI unit and meter per second square is also the SI unit. So what I can write, so F is equal to total 5 into 4, it's 20, right? And how many zeros are left? 1, 2, 3. 1, 2, 3. How much it is? It is 20,000. Force SI unit is Newton. So force value is 20,000 Newton and acceleration is 4 meter per second square. In that way, numericals can be solved. You may think that why this much space is left over here? Now, another model of questions can be asked. Basics. Let's see this example here. There is a ground, a body of mass, you can say some 2 kilogram is kept here. From this direction, there is 10 Newton force is acting, right? And in this direction, the body is moving with an acceleration of 4 meter per second square. There is a force acting in this direction. Identify what is that force acting in this direction. That may be 0, or that may be 2 Newton, 5 Newton, whatever it may be. Our question is this one. Okay. Now, how to do that? First thing, mass is there and acceleration is there. You can do F is equal to ma. Here comes the concept F. Here F is not only the 10 Newton. Here they have clearly given that another side is also, there is a force F. So this F means what? The net force here. Always in your F is equal to ma, just try to go back and check at the time of F is equal to ma, what I told, this F is the resultant force. It's not a single force. When there is a only single force acting on the body, that is equal to the resultant force. But here, there are two forces are acting. So the resultant force must be written here. So what is the resultant force in this case? So acceleration direction is given in this direction. That means this is greater. 10 Newton minus F. So that's the resultant force. 10 minus F, because both are in opposite directions, which is equal to mass is 2 kilogram into acceleration is 4. Okay. Now 10 is equal to, so this is 4 into 2, it's 8, and this is minus F can be written to the other side, that will be plus F. Now what I can write? 10 and this plus 8 taken to the other side, that will be minus 8, which is equal to F. So tell me, F is equal to how much? It's 2 Newtons. Like this also questions can be asked. Be prepared and be ready for that. Now, one more type, let's see, one more type. So this is an example. Now, this is the ground. You know, my own design of the car, you know, I'm just writing it, don't be afraid. So day by day, my design will be improved. Okay. Now, this is the car. Initially, the driver is moving with an acceleration of A1, first case, the acceleration it is moving with 1.8 meter per second square. After some time, the driver is moving the car with an acceleration 1.2 meter per second square. The car is same. The force is acting is different now. Understand? The accelerating force, what acting on the car is different in the two cases, but the mass of the car is m only, right? Sometimes the car, we move slowly and we move faster. So it depends on the traffic or the road, whatever it may be, the opposition, right? Now here, acceleration of the car, initially it's 1.8 meter per second square. After some time, he is driving the car with this acceleration. Now the question is, what is the ratios of the forces in these cases? So the question is to find F1 by F2. So simple. F1, M1, A1 by F2, M2, A2. Mass is same. With the acceleration, mass of the car will not change. So mass is same. So F1 by F2 is equal to A1 by A2. So what is A1 here? 1.8 meter per second square by A2 is 1.2 meter per second square. Meter per second square cancel. And here 1.2 is here and this is 1.8. And for example, 0.62, 0.63 is 3 by 2. F1 by F2 is how much? F1 by F2 is how much? 3 by 2. And the another way of solving the same question, the another way of solving is, if I write F is equal to ma, here there is a change is taking place between acceleration and force. Anyhow, mass remains same every time. So then I can write F is directly proportional to A when mass is constant. So from here, F1 by F2 is equal to A1 by 8. Okay, so this is what according to the rule of proportionality. When A is directly proportional to B, its ratios also will be equal. A1 by A2 is equal to B1 by B2 when A is directly proportional to B. This is how a basic numericals can be asked, right? So let's move into the another topic of Newton's second law of motion only. So that I will reveal in the next class. See you soon.